Hello, everybody. My name is Boredom Isaac Berry, and today we'll be talking about analysis. Now, all of my understanding of analysis comes from Ziri Levels. Now, I know I probably mispronounced that. I'm sorry. But Ziri Levels' Introduction to Real Analysis. It's a very great book with some great geometric intuition, so you should go look at it. And some of the things that we'll be doing today come directly from there, but others come from the understanding I've got from my previous courses and previous books that I've read. So when I say functions, what do I mean in specific? Well, your Algebra 1 class has probably taught you that a function is something you see on a board like this, on a coordinate plane, like y equals x squared, or y equals 2x, or y equals sine x. But it turns out that this is not a very rigorous definition. A line on a plane. Yeah, I mean, that could be anything. So, what does a function mean in specific? In fact, it's not even directly associated with the coordinate plane. A function is like a computer program. It takes something in, it does something to it, and it spits that thing out in a different form. So, for example, take f of x equals 2x. What does this do? It's not just a really steep line on the xy axis, even though that's what you may have learned it is in Algebra 1. What it actually does is it takes our original number and it spits it out, adding it to itself. So we go from n to 2n. So this is the basics of how a function works. It takes in something and it spits out something else. Now, when we talk about domain and range, what do we mean by that? Let's take, for instance, square roots. So these are some of the most basic functions with limited domains. And when I mean limited, that means they're a subset of the real numbers, a proper subset, by the way. So let's say, for example, we have the square root of x, keeping it plain and simple. So our factoring machine right now takes in a number and spits out its square root. So for example, I put in 4, it spits out 2. I put in 9, it spits out 3. But keep in mind, since we're only discussing the real numbers, what happens if I put in something like, I don't know, -3? What happens then? Well, it's like this thing gets jammed in the printer. It can't come up with a result. So, in this case, the function can't map the input -3 to any sort of value. So, the domain are all of the numbers that this printer can process without being jammed, that this factory can take in and produce a result. So, essentially, a domain is any number n such that so it contains all of the numbers n and nothing else, such that f of n exists. And how about a range? Well, a range is a bit different. So a range can also sort of be explained by a square root, but a better analogy is sine. Sine, cosine, any basic trigonometric function you want. So this is just an approximation of f of x equals sine of x, right? Now, hopefully we all know the definition of sine, but as you can see, since sine is defined on the unit circle, that means that it cannot get any higher than 1, and it cannot get any lower than -1. In other words, let's say, I want to make this a different shape. Let's say this is our factory, and you want to put something in, you don't know what that is yet, so that the result that comes out is the number 2. But there is no such thing that gives the number 2 because it's limited between 1 and -1 by definition. So, for example, if you want the number that spits out the square root of 3 over 2, you'd plug in 60 degrees, or pi over 3 if you want radians. But if you want the thing that spits out 2, it's not like there's anything you can put in to get this out, is there? So the range is the number of possible products that this factory produces. It's all of the possible products. But these are some very basic definitions. So now let's get to the first really challenging subject. What is continuity? Now, you might think continuity is very simple. Your Algebra 2 or pre-calculus teacher probably told you if a function is continuous, you can draw it without taking your pen off the paper.
Right.
Now, is that a rigorous definition?
It is.
Not at all. I mean, what's a pen mathematically? What's a paper mathematically? We have nothing in this mathematical world. So, I mean, also, if you do some very technical shenanigans, you might be able to perfectly draw a line up and draw this function, even though it's totally discontinuous. Or maybe your pen runs out of ink, and then you suddenly miraculously come back with ink after a certain point. So, I mean, how much you can draw without taking your pen off the paper, that's a totally ridiculous definition. So, what is continuity really? A function is continuous over some interval, I equals from A to B, if and only if at every single point f of c is equal to the limit as x approaches c of f of x. But then, what's a limit? I mean, you might say where we think it's going based on how closely we look. But that's not a very rigorous definition either, is it? So we need a formal definition of the limit. And that's where the epsilon delta definition comes in. I have no way to erase that board. It doesn't really work well. And that's where the epsilon delta definition comes in. No, this eraser doesn't work on that board.
You want to give it a try? Bigger space. Yeah, good enough.
Sorry, this is just my practice for the lecture. So, what is continuity? So what is a limit? Well, a limit is defined by the epsilon delta definition. Imagine taking a function right over here. And what we mean when we illustrate it on a coordinate graph is we have some function on the number line c, and essentially we map it vertically to a different number on the number line, f of c. And then the point we get from the horizontal and vertical lines meeting is where the function is at that point. And more often than not, that tends to form a continuous line. So let's say we want to figure out the limit of this definitely continuous function at, say, c. How would we do that? Well, essentially, we say the limit as x approaches c of f of x is equal to some number L if and only if for all epsilon greater than 0. So epsilon is any arbitrary number. It can be arbitrarily small. It just has to be positive. So for all epsilon greater than 0, it cannot include 0 for reasons you'll see in a minute. The limit as x approaches c of f of x is equal to L if and only if for all epsilon is greater than 0, there exists, I'll write it down in full, there exists a positive delta, also arbitrarily big or small, such that the distance between f of x plus delta, not f of x, f of c plus delta and f of c is less than that specific number. No, I'm done. There exists a delta greater than 0 such that the distance between f of x c plus delta and the limit L is less than epsilon. In other words, let's say we zoom in on the point C, which is right over here. Zooming in right there, let's say epsilon plus minus epsilon is this small region over here. Well, we can still find some small deviation. I'll draw the dotted line. You can still find some small deviation delta, such that f of c minus delta or f of c plus delta is still within that tiny epsilon range provided. And the proof of the limit existing is that no matter how small it gets, from both sides, we can find that limit existing. So that no matter how small epsilon gets, from both sides, we can find an existing delta. Now, why can't epsilon be 0? Well, great question. That's because, what if there's a hole? Now, you probably have no idea what I mean by that. You probably do have an idea of what I mean by that if you've taken Calc 1, but still you probably have no idea how it connects to the main plot. So what if there's a hole right here? What happens? Well, in that case, if epsilon is equal to 0, then delta is forced to be equal to 0. But then f of c minus L, if there's a hole here, this is probably a pretty big distance, or even infinite, or it probably doesn't exist. So then there's no way it can be less than epsilon, meaning even if everything around it clearly converges to a limit, this itself will prevent it from converging. So that's why we can't have epsilon or delta equal to 0. All right, so now we know what a limit is, and now we know what continuity is. Continuity basically means we can, given some slices of the function near a point, we can predict pretty precisely where the function is approximately going to be in that interval. Or more precisely, we know that the limit where we think it's going as x approaches c is equal to where it's at c. That's continuity. So that's one of the 3 big things that we want to cover. Now, let's start talking about derivatives. But before that, let's start covering some more strong kinds of continuity, because this is the easiest layer of continuity to satisfy. But next, we'll get to uniform continuity, which is a little bit more difficult to satisfy. Now, uniform continuity guarantees continuity, but not all continuous functions are uniform continuous. One surprising example, actually, y equals x squared is not uniformly continuous. Why is that true? I mean, clearly we can tell where it's going, right? But here's the problem. Let's say we want to try and enclose wherever it is right now in a little box. And we keep dragging this point along, and we keep dragging the box with it. At some point, this point is going to leave the box. Oh, and I should probably be clear that the box is perfectly centered on it. Now, obviously, this has no meaning unless I mathematically define it. So what I'm trying to say here is that there exist two fixed numbers, epsilon and delta, greater than 0, such that if f of x plus minus delta, such that for all x, f of x plus minus delta is between f of x minus delta minus epsilon and f of x plus epsilon. In other words, the amount of change that a small change makes is always bounded. Or in other words, well, no, that's basically the best words I can put to describe it. But Wikipedia also has a great image on how to visualize uniform continuity. And finally, there's a last, really strong layer of continuity, Lipschitz continuity. So what's Lipschitz continuity? Well, that just means that the slope, the derivative, is always bounded. So that means that some very surprising functions that pass the uniform continuous test, like for example, y equals the square root of x, we can draw a secant line right over here, and it'll keep going up. And we can draw a secant line smaller and smaller, and eventually it's going to approach parallel to the y-axis. In other words, as we approach 0, the slope, the derivative, approaches infinity. And that is not what Lipschitz wants. In other words, as Wikipedia puts it, we can take a double cone centered at the function, at a point in the function, so a double cone like this, and we want to be able to trap the entire function in that cone. And if that isn't satisfied, if there's no such double cone for which this is possible, or if that double cone is the entire plane, then it's not Lipschitz continuous. So these are the three different levels of continuity. Now, let's get to derivatives. What the heck is the derivative of a function? F prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x over h, which you probably remember or recognize from a very long time ago. This is the ultimate final formula. Now, this isn't very helpful in the long run, which is why